So we have the simulation, but as you can see, as soon as these guys goes into ragdoll, they're just falling apart. And of course, most of the time when you're working with ragdolls, you don't want that. You want the different limbs to stick together. So let's take a look how we can do that. The first thing we do is go into the agent setup, and I'm gonna drop down an agent configure joints. And in here you can define different joint limits, but I'm not even gonna do that for this example. Just by adding this, we get these attributes added. And you can see if I turn that off, we don't have them, and then I turn them off. So we get these attribute arrays. And these are useful for the next node we're going to drop down here in the crowd layout, and that is the agent constraint network. And the first port is just piping out the agents, and in the second port it creates the constraints. So if we visualize the second port, you can see we don't have the agents because it's just a constraint. But let's see what the constraints are then. First, at the point position, we have the anchor points. And so every anchor point, they define what is sticking together. So here is the point position, and we can see if I visualize this, we can see we have all these points here. So here we have the point position, and at the end here, for the name, we have the agent, which is agent 0, so that is agent number 0, and then it's defining what body part this anchor point is for. So in this case it's a hat, and here is agent 0's head. We can see that these points have the same point position. So if we go and just take a look at that, so if I move one of these points, you can see that it's actually a line. It's just that both the anchor points are at the same position, so you don't see that it is a line, but it is actually a line. So let's go further. So we have this first anchor point, which is the hat, and the head is connected. So here in the vertices we can see that primitive 0 have two vertices, 0, 0, 0, 1, and 0, 0 is point number 0, which is this one, and 0, 1 is point number 1, which is this one. And if you go to the next one, you can see for primitive 1, the vertex 0 is 2, which would be this one, and primitive 1 is 3, which would be this one. Alright, so that defines what points each polyline is made up from. So let's go to the primitives then. So let's look at primitive 0. And here we can see we have like all these attributes. And in our case, because we are not using the joint constraints, a lot of these attributes doesn't make any sense right now. So most of these attributes are defining the joint limits. But in our case, we're going to use this built-in. If we look at the agent constraint network, we have this checked, pin shapes with no rotational limits. So what this says, if we haven't defined any rotational limits, then this is going to make a hard constraint. This calls this pin, but it's going to set up a hard constraint. If you use the crowd tools and setting up a ragdoll network, this would be a hard constraint. The most important thing for us here is the constraint name, which is pin. We need to remember that. And the constraint type is all, which means that it affects both the position and the rotation. What the hard constraint has to do is try to make sure that these two are sticking together, but you can actually, if you apply a lot of force to it, make it overextend. But we can talk more about that later. For now, we just can see that all of these guys are going to be hard constraints. So the next thing we need to do, let's remove this guy, is to go into the DOPSIM here, and then we're going to set up a hard constraint. So first of all, I'm going to drop down a constraint network. This is telling our crowd simulation that we have constraints for the different agents. And now it's erroring out because we need to give it a couple of things. First of all, we need to give it a constraint. So let's do a hard constraint. Do a hard constraint relationship. Got to plug that into here. Here for the rest length on the hard constraint, as you might remember, the two anchor points have the same position, which means that they have a rest length of 0. So we're going to set this to 0. And let's also point to the constraint network. So let's go into here and go to crowd layout and out constraints. So one thing we need to do, because remember when we looked in here in the spreadsheet, we have this constraint name. So we need to tell this hard constraint that is the name it should use. If we take data name and put this to pin, now it knows that every primitive with that attribute is a hard constraint. So if we look at this now, we can uncheck this display geometry, and here we can see that it has applied 3 hard constraints on each agent. And you can see it's not on every point here. It's just going to put a constraint between every collision geometry. So it's going to be one between these guys and one between these guys, and then one for the hat. So let's go back here. So here you can see that they are constrained together. And let's go back and just turn that back on again. If we play this now, you can see that all these snowmen are holding up together. So now they're just acting like some small stiff units. Cool. Just to break it up a little bit, we can say like, oh, we don't want all of them to be a unit. We want some of the pieces to break apart and some of them to stick together. So let's do it in a very quick and easy way. If we go to crowd layout, and I'm going to drop down randomize attribute. We'll call this break. It's a primitive attribute. We're going to have it in one dimension. We're just going to have it as a float. And it's between 0 and 1. So if we look at this now and take a spreadsheet, we can see that the break goes between 0 and 1. And now when I have this, I'm going to drop down and blast. And then I'm going to say this break is greater than 0.5, which means half of the objects, then delete that primitive. So if I do primitives, look at that, you can see now it deletes half of them. What that means, you have all these primitives that defines that it's a hard constraint, and we'll delete half of them. So some of them won't exist anymore, which of course means that some of them are going to break apart now. So if we play this, you can see here the hat is falling off. These pieces are still together. All these three are together. So now it's completely random what part is holding together or what's breaking apart.